Now let's look at the number of possible candidates for a nominal variable. So a nominal variable, since the ordering is not important, like for example the ordinal variable that we saw before 1, 2, 3, 4, where we couldn't mess up the ordering, but if 1, 2, 3, 4 is a nominal variable, then the ordering doesn't matter. So you can have any number of ways in which you can split. So that results in even larger number of possible candidates, and it gets a little more complicated. So this is the formula that we can use to figure out. So if there are L possible values for the nominal variable, and if you're looking at B splits, okay, so if you have L possible values, then you can have two-way split, three-way split, four-way split, five-way split, all the way up to L-way splits. So you have to now start with 2, 3, and 4 and calculate S, L comma B for each of the possible values of B, and then add them all up. Then that will give you the total possible splits for nominal variable. Now we will not list all of them. So for example, if you take the case of 4 levels nominal now, not ordinal, like previously 4 level ordinal that we saw previously. So now B can be either 2, 3, or 4, right? So if B equal to 2, you get 7 possible splits, nominal splits, right? There is two-way splits. There are 7 possible binary splits. Three-way splits, there are 6 of them. 6 possible three-way splits. And when B equal to 4, the four-way split, there is only one way we can do that, because you can put 1 on one branch, 2 on the second branch, 3 on the third branch, 4 on the fourth branch, and there is only one way we can do that. So we take each of the possibilities. So there are 7 binary splits, 6 three-way splits, and 1 four-way split. So that gives you 14 possible splits. Okay, now here are the list of possible splits. So binary splits, so 1, 2, 3, 4, 2, and then 1, 3, 4. See, the ordering does not matter. So 3, 1, 2, 4, and so on. So you have 7 binary splits, and then here are the 6 three-way splits, and then this is the one single four-way split, adding to 14. As L increases, okay, so if you have 2 possible values, 3 possible values for the nominal variable, 4 possible values, and so on, so you have to figure out how many possible splits are there for 2, 3, 4, 5, and as we go higher and higher, more branches are possible. But suppose if we restrict ourselves to only up to 5 branches, right? So beyond 5 possible values, we will restrict it only up to 5 branches. Now you see the splits increasing in a much faster, total possible splits increasing in a much faster and larger way. Now if you plot this, then you get a curve in this fashion. So when you get to about 15 or 16, after that it just takes off. Now if you plot both the nominal and the ordinal charts in one plot, okay, so here, so splits for ordinal and nominal. So here is the ordinal variable number of possible splits as L increases, and this is the nominal. So you see the nominal results in tremendously more number of splits. So you have to be really careful about this. We'll talk more about this in a little bit. So these are the possible number of candidate splits that you have for one variable, okay, one ordinal variable or nominal variable. So the combinatorial explosion usually makes an exhaustive search prohibitively expensive. So you're not going to sit there and do all possible splits. So you have to come up with a more intelligent way to reduce the number of possible candidates. and that's what is implemented in most software packages. But we will look at exhaustive search first with a simple example, and then we will look at how to, the parameters with which we can tune our modeling so the number of possible candidates for split is not too high or prohibitively expensive. Okay. Well, here are the strategies that we can follow to limit the number of splits. So one possibility is to say, okay, we're going to limit only to binary splits and nothing else. And then you can impose minimum child size restrictions. So minimum categorical size restrictions. Use input only once. And then you can do within node sampling. So let's look at these. So limit searches to binary splits, that's the default in SAS Enterprise Minor. And the benefits is the exhaustive search is possible because fewer splits are considered. So if you limit yourself to only binary splits, then you can consider all possible binary splits. And also when you do multiple branches, more than two splits from one single node, then you end up depleting the data very quickly. That's actually starving. So that should be a limitation actually. So multi-way splits give trees that are easier to interpret. Okay. Well, actually, yeah, multi-way splits will deplete the data, which does not happen in the case of binary search. So that's a benefit. And multi-way splits give trees that are easier to interpret. So that's kind of a limitation when you restrict yourself to binary search. And multi-way splits predictors are used fewer times in the tree, repeating a given predictor second time and a third time, so that happens less often in a multi-way splits. In binary, it may happen more often. Okay. Minimum categorical size, and that is how many observations are there for each category. So for a predictor variable, so suppose if it is a nominal variable, say green, red, blue. Okay. Now each category must have at least a certain number of observations. So the default minimum is 5. If a particular category, particular value of a nominal variable has less than 5 observations, then SAS will automatically treat those observations as missing values, and so it will not be considered as a valid value. But actually, when you have a nominal variable with 20 different categories, and some of them have very low observations, instead of making them missing values, you can combine the categories into larger groups. If they are combinable. If they are not combinable, then you have to mark them as missing values. But decision tree will handle missing values. You don't have to impute like in regression analysis. So missing values can be easily handled by the methodology itself. And then you can we looked at limiting binary splits. Okay, impose minimum categorical size. These are the two that we discussed. Here, impose minimum child size restriction is one way of limiting the number of searches. Is when you branch out, okay, in the left side branch and the right side branch, you can say, okay, the rectangles must have at least X number of observations. So like 5 or 10 or something like that. So if it has less than that, then you don't consider that split. So that will also will have an effect of limiting the number of candidate splits. And one other is to use input only once. So a given predictor, once you use it in a tree, then you don't use it again. That's not a good idea though. So that you're limiting yourself in terms of modeling the signal in the data. So this is something you should not do. Okay. And then you can do within node sampling. So you take sample within the node and not consider all of it. So you get just random sample and then use only those values for splitting. Again, that's not a good idea. You can use these three to limit the number of possible candidate splits from becoming excessively large.